Okay, in this video here, we're going to be talking about elimination reactions. Two primary elimination reactions we're going to look at. The first one is the one at the top. It's called dehydration. It involves an alcohol. And what we do here is we take an alcohol, we basically rip water out of it, and we produce an alkene. Okay, in this bottom reaction, it's very similar, except we're using an alkyl halide, and we're taking X and H out of the molecule to also produce the alkene. And the top reaction's often catalyzed by an acid, whereas the bottom reaction usually requires a base. Okay, let's look at some fundamental characteristics of this reaction. First, let's look at this what we call the alpha-beta nomenclature system. Okay, alpha just means this is our carbon of interest. Obviously, it's not an IUPAC term or anything like that. It's just a formal way that chemists talk to each other. Okay, beta is the carbon beside the alpha carbon. Okay, so if we look at dehydration, where does our water come from? It comes from plucking an OH off the alpha carbon and an H off the beta carbon. OH, H2O, is removed from this molecule. Okay, a very similar thing is happening in dehydrohalogenation. X is removed from the alpha carbon. H is removed from the beta carbon. This reaction needs base, and this reaction is not catalytic in base. It needs a whole mole of base, okay? Because you've got all this base around and you're producing HX. We don't actually make HX. We make the halide anion and the conjugate acid of whatever base that we use, okay? All right. So if we look at this bottom reaction, what are its limitations? Well, X has to be chlorine, bromine, or iodine. And a lot of the reactions of halides, this is going to be the standard limitation that you see. Fluoride is just not that reactive. The carbon-fluorine bond is incredibly strong, and it's very difficult to break it. There are other reasons why fluoride doesn't work as well. Okay, so in this video, we're going to focus exclusively on the acid-catalyzed dehydration process. Okay? All right, so here's some examples of acid-catalyzed dehydration. What you see is very different, or slightly different conditions, but all of these are using a very strong acid and heat as the reagent system for ripping water out of these molecules. This combination you see at the top, sulfuric acid and heat, this is the most common reagent system that you'll see doing a dehydration reaction. Okay, so cyclohexanol reacts with sulfuric acid and heat to make cyclohexene. In this next equation here, we're using not sulfuric acid, but the conjugate base of sulfuric acid, which is still quite a strong acid. Right away here you see a little bit of a complication. We're making several products. We're making, as our major product, 2-hexene, and as our minor product, 1-hexene. And of the 2-hexene that we make, it's mostly the trans isomer. There's more of the trans isomer than there is of the cis isomer. Okay? All right, so when we look at the structure of our alcohol, right away we can see the source of this problem, right? Here's our alpha carbon, but we see we only have two different beta carbons, beta and beta prime. This comes from removal of the hydrogen at beta, and this comes from removal of the hydrogen at beta prime. Okay? Let's look at the bottom one. The bottom one's also unsymmetrical. Here, there's tertiary alcohol. You have the alpha position. I have beta, beta prime, and beta double prime, but beta and beta prime are equal to each other. Right here, we see that the major product is 1-hexene, and this other product with the alkene outside the ring, which we'll just refer to as the exocyclic alkene, is a very minor product in this reaction. Okay, hopefully you see a trend here, that in both cases we produce the more substituted alkene. And this is called Zaitsev's rule. It's just that dehydration is going to produce the most stable alkene. Right now, the only thing that we've seen that affects alkene stability is, of course, the degree of alkyl substitution. So right now, we can say that we're going to produce the most substituted alkene. That's going to be the one that's most stable based on what we've seen so far. Okay, we can also say that we're going to produce the alkene that has the fewest hydrogens attached to the alkene carbons. Okay, so up here we're producing the one that has 2 hydrogens. Over here we're producing, as a minor product, the one that has 3 hydrogens. Okay, and same thing here. The major product has only 1 hydrogen, whereas the minor product has 2 hydrogens. So that's another way of saying Zaitsev's rule. Now, later in this course, we're going to encounter other things that affect alkene stability. So we're going to have to remember that it is the most stable alkene. But for right now, alkyl substitution is the one thing we know that's making an alkene more or less stable than another alkene. Okay, so let's do just a simple prediction here. This is a problem for you. Predict the major product of each of these reactions. Pause the video, do it, and then restart it, and you'll see the answers. Okay, so what's going to happen in this first one? All right, so if we're producing the more substituted alkene, we know that one of the alkene carbons is going to be this one, and the other one could be either that one or that one. And of course, we'll call this beta prime over here. We're going to get the more substituted alkene by removing the hydrogen that's at beta, right? Okay, so we get the more substituted alkene by removing that hydrogen. There's our major product. Oops, I've got them all here, sorry. All right, so when we look at this next one, here's alpha. This beta carbon, we can't really use it because there's no hydrogens here. We're going to see how that may not be all that big of a limitation in a few minutes, but for now, in this type of system, it is a limitation. We can't form an alkene on that side because there's no hydrogen to get rid of. All right, so we have 2 sets of beta hydrogens, one from the CH2 over here and the other from the methyl group. Plucking one of these hydrogens here off, along with OH, gives us the more substituted alkene, the product that you see over to the right. Okay, this is kind of like 2-butene. I just put a chlorine in there for fun. But plucking on the beta side will give us the more substituted alkene. The chlorine is not a part of this reaction with acids. As we'll see, it's amenable to treatment with base, but not acid. Okay. All right, so let's look at the mechanism for this reaction. First, let's look at its relative rate. The rate is tertiary alcohols are fastest reacting of all. They're faster than secondary, faster than primary. Where have we seen this reaction order before? That's in the marquee reaction of chapter 4, right? when we reacted alcohols with HCl, HBr, or HI to get the corresponding alkyl halide. And we remember that that reaction went through a carbocation. Another important fact about this reaction here is that it's potentially reversible. So the reaction that we see going to the right is the reaction that's featured in this chapter. We're going to see some discussion of the reaction that's going the other way in the next chapter, chapter 6, where we can add water to some alkenes under acid catalysis to make alcohols. Okay, this reaction is really governed by Le Chatelier's principle that if you do something to affect the equilibrium, the system will adjust itself to maintain equilibrium. So the way we typically run a dehydration reaction is actually to remove water from the system as it forms. So often this is done at a temperature higher than the boiling point of water so that it will leave during the reaction and the equilibrium will go that way. It's a little bit harder to make the reaction go to the left. It's not really all that reliable. Okay, but I'm going to show every step as an equilibrium step to illustrate that principle. Okay, so in step 1, it's exactly like it is in that previous reaction in chapter 4 where it reacted with HBr, for example. We're doing a reversible protonation of the alcohol to produce the oxonium ion. Again, this is just an alcohol substituting for water in the Bronsted-Lowry equation. Okay? And we expect this reaction with a very strong acid like sulfuric acid to go to the right. In step 2, this is our rate determining step. The water leaves to make our old friend, the carbocation. Okay? And water. This is where our byproduct water comes from in this step. Okay, in our next step, we're going to use water as a base to remove a proton. Okay? Instead of adding here, this would just take the reaction back to where it started. Water removes a proton from the beta carbon in an acid-base reaction, and this electron pair that used to be a CH bond now becomes the pi bond of the CC double bond. Okay? All right. Now the reaction is catalytic in acid, so what happens here is that the acid that we generate in this step goes back, of course, and restarts the whole business. Let's draw the arrows properly. Sorry, okay. That way the reaction starts over again. Notice that in the first cycle, sulfuric acid is the acid, but in the next cycle, it's probably H3O+. All right, why is it that I used water here to remove this proton and not the bisulfite anion? Well, this is actually the stronger base. Okay, and you can infer that from the fact that in the Bronsted-Lowry equation, water plus sulfuric acid goes to the right to make bisulfate anion and H3O+. So therefore, water is the stronger base. Okay, notice that in this carbocation intermediate over here, we have 3 beta positions. Beta 1 and beta 2 are equal to each other. Beta 3 is different, but if we remove the hydrogen here, we would get this minor product. Okay, so that's not usually the preferred pathway. The preferred pathway is removal of the hydrogen at the more substituted carbon, so you'll get the more stable alkene. I should say a little something here about rate equations too. I'm not sure I've put it in a future slide, but the rate Okay, it's a first order reaction. Okay. All right. Here's a kind of an unusual case here, and this is where you have to really pay attention, okay? A lot of people say that organic chemistry becomes a hard course when the carbocations start rearranging, okay? And this is an example of something called a rearrangement reaction. This alcohol on the left, when treated with sulfuric acid, produces what you would probably expect to be the major product. This one here is only a minor product. Okay, so this is from removal of OH from alpha and H from beta, like you've come to expect should be the way things should go. But unfortunately, this is only a minor product. The major product is very different from that. It's actually, if you look at the beta, alpha, beta nomenclature system before, we're actually putting the double bond in what would be formerly the beta and gamma positions, not the alpha beta position. So this system has done something that we call a rearrangement. And this is a fundamental problem with carbocations. It's really caused by the hyperconjugation. All right, so let's look at the mechanism for formation of this product on the far right. The reaction starts out exactly the way the previous one started out. The first two steps are identical. Sulfuric acid protonates the alcohol to make the compound. Here, the protonated alcohol, we lose water and we make the carbocation. One thing that this carbocation can do is lose this hydrogen right here, and this results in our minor product. Okay? But look what would happen if this hydrogen right here and its electrons moved over to here. Okay? And we're going to call this process a 1,2 hydride shift. Something wonderful happened in this 1,2 hydride shift. We went from a secondary carbocation to a tertiary carbocation. And so we've increased, or the energy level of our system has gone down by doing this. We've produced a much more stable carbocation. The major product forms from this carbocation right here. We're just going to remove the hydrogen from this position because this position is going to give us the more stable alkene. Okay? I don't know this minor product. Where does it come from? Does it come from this way I've indicated here? It could also come from just taking this rearranged carbocation and removing this hydrogen right here and producing the compound as well. There are two different pathways for making the minor product. Okay, so this 1,2 hydride shift happens because of hyperconjugation. Recall that in hyperconjugation, we're basically partially donating the electrons in this bond over to the p orbital. So this bond is essentially become a lot weaker. It's partially broken as a result of hyperconjugation, and thus it's really easy for it to move. Okay? All right, so in general, if you can produce a more stable carbocation by doing a 1,3 hydride shift, it's very likely that that process is going to occur. Okay, let's look at another system that's going to do rearrangements. Okay, here we're seeing the actual carbon skeleton change. If you look at the starting material, there's only one beta carbon that has any hydrogens at all on it, right? And that's this one. Okay, this one has 3. Oh, sorry, I didn't need to do that. I already drew those. Okay, so sulfuric acid and heat could produce the compound where the alkene is at in the alpha and beta carbons, but right away you see that that's not what's going on here because that's only a minor product. The two major products that you see in this reaction involve one of the methyl groups actually moving over, okay? So notice here that this carbon here, which we'll call beta prime, has 3 methyl groups on it. But over here, no carbon in the system. Has more than a couple of methyl groups on it. So clearly one of the methyl groups is migrated. Okay, a very similar mechanistic process is occurring. Again, the first 2 steps of this are the same as the previous slide, which are the same as the simple system before that didn't rearrange. We're protonating the alcohol and losing water to make a carbocation. This carbocation is secondary, but imagine if we now move this methyl group over to here, we generate a tertiary carbocation. And again, this is also occurring due to hyperconjugation. Okay, the carbon-carbon bonds can be engaged in hyperconjugation just like the CH bonds. Okay, so after this rearranges, we can take this hydrogen. Remember that it's actually been here the whole time. And that hydrogen is the one that actually goes away to make the final product. Okay, so in general, if a more stable carbocation can be created through a 1,2 hydride or 1,2 alkyl shift, the process is very likely to happen. In most cases, the hydride shift is going to occur faster than the alkyl shift. But if we have a system like this, we'll call it carbon 1 and carbon 2, where carbon 2 is quaternary. Okay. Recognize that if we have 3 different groups, any one of these 3 alkyl groups can do this rearrangement. Okay, so over here the ethyl migrates. Okay, if we look at this one, isopropyl is migrating. And in this last one, methyl has migrated. Okay, when the adjacent carbons are part of a ring, you actually change the ring system quite a lot. Okay, so let's look at this one. Over here, we have to regard each of these CH2 groups as just another alkyl group. Okay, so they can move over just like any other alkyl group. All right, so there's 2 possible products from migrations here. We can make this one if methyl migrates, and this one if CH2 of the ring migrates. Okay? All right. So either of these 2 are possible, but you might think, shouldn't the second possibility be the favored one because of angle strain, and that's in fact quite true. Here we have a four-membered ring. And over here, of course, it's ring expanded to give us a five-membered ring. So in this case, this is what we call a ring expansion reaction. And this is actually quite favorable because there's a relief of angle strain when this CH2 group migrates. So because of this, you're probably going to see the CH2 migrate instead of the methyl. If the methyl migrates, you've still got the angle strain of a four-membered ring. Actually, it's even worse because the carbocation's sp2, and you don't want to put sp2 carbons in rings. Okay? All right, so that's just a statement that says what I just said there. The second pathway is more likely because there's also a relief of angle strain. Okay, in each of these, this is a problem now. You should do it, pause the video, do it, and then check your answers, but let's just go through this. State whether each carbocation rearrangement is likely to occur. If you think it will not, state what's wrong with it. Okay, so let's look at this one. What we're doing is we're taking this hydrogen here and we're moving it over here. And if we look, number the carbons, we see that this is a 1,3 hydrogen shift. And this is not going to occur because we only do 1,2 hydrogen shifts. Okay, so this first one is not going to be very likely. Okay, the second one is a primary carbocation. It's not a very stable one. We're looking at it possibly rearranging like that. If we look at what happens to the carbocation stability, primary becomes tertiary. I like to say also, let's just remember here that secondary became tertiary. So that's good in that respect, but not so good because it's a 1,3 shift. If you look at the shift, it's coming off of the second carbon or the beta carbon, so it's a 1,2 alkyl shift. And it's a 1,2 alkyl shift producing a more stable carbocation. It's wonderful. It's supposed to happen. Okay, in this last one, we're moving this set of this CH2 group here, and we're creating a, looks like we're moving this CH2 group from this perspective, sorry. Okay, this is creating a secondary carbocation when we started with a tertiary carbocation. If we look at the carbons involved, of course, it is a it's a 1,2 alkyl shift, but it's producing a less stable carbocation, so it's not as likely to proceed. So this one's unlikely because it's a 1,3 hydride shift. This one's very likely. A more stable carbocation forms, and there's also relief of angle strain, and it's a 1,2 alkyl shift, which is the type that's allowed. This bottom one, unlikely because a tertiary carbocation is transforming to a secondary carbocation. Even though it is a 1,2 alkyl shift, it's resulting in a less stable carbocation. And I believe this is the last one in the dehydration. Write a mechanism for the following reaction. It's a little bit more complicated than what I put on an exam because it's forming three products, but we should be able to figure out where these come from. And again, you should pause the video and do this one yourself. Normally, if I put this on an exam, I would allow you to just use H plus instead of H2SO4. And sometimes I would give you a little hint by just drawing the lone pairs at oxygen. Okay? All right, so what is the mechanism? The mechanism starts off, remember, just like all dehydration reactions, we do a reversible protonation to form this protonated alcohol here. We lose water to form our initial carbocation. The easiest product to figure out, of course, is the top one, because that is just the simple dehydration product without any sort of rearrangement whatsoever. We're removing the hydrogen from this position right here. Okay, we'll just draw those in, and we're removing the hydrogen from the beta position right there. Okay, one of the things that this could do, just like before, is that it could migrate the methyl group. Okay, so if the methyl group migrates with its electron pair, we're going to get the carbocation over here. And I'll explain right before we end this what are some common mistakes that students make when they write the mechanism. So hopefully you won't make those mistakes. Okay, so once the methyl group migrates, we can remove this hydrogen right here, and this gets us the product that you see there. Okay, the one that still has a 7-membered ring, but the methyl groups are in different positions. The last one is a little bit harder to see than all of the others, so I've given you a little bit of a hint as to what's occurring. Okay, so the key thing to note here is that carbons 3 and 4 are connected in the starting material, but in the product, carbon 4 is connected to carbon 2, and that's where our rearrangement is occurring. Okay, so we can also get a tertiary carbocation by migrating the other carbon that's, again, technically the same as the methyl groups. Okay? All right, so we're going to migrate the CH2 group of the ring. This means the carbocation is now outside the ring, but it's tertiary. Okay, so both of these are good processes because they create tertiary carbocations. And the final product occurs by removing the hydrogen right here. Okay, so what are some of the mistakes that students make when they write mechanism problems like this? Okay, mistake number 1. This intermediate here is actually quite important. You should show all of the energy minima along the reaction pathway, and that's a key intermediate. Failure to show that will cost you a couple of points. All right. What's another thing that students do? In these very symmetrical systems, a lot of times people will show not the product I have indicated right there, but they'll show something like this. And technically that's the same product, but if you look at the perspective, how it's drawn, look at how the 7-membered ring is oriented, how a carbon's down here and a carbon's at the top. It implies that the person who drew this didn't realize that not only do you migrate the methyl group, but you also have to migrate the position of the positive charge. So this Again, this is a symmetrical compound. You couldn't really tell that. But this is a situation you want to avoid. In this last case, you actually can tell the difference, because if somebody's making that mistake in that one, what they'll draw as the product or the rearrangement product here is that. And this is wrong, okay? Because if you look at the migration, there's 3 bonds to carbon here and a positive charge. It's getting another bond, so there should be 4 bonds to this carbon, right? And there's only going to be 3 bonds to this carbon out here. And this is just not the right way. The hydrogen here should be where the carbocation is. This is correct here. Okay, so this is a common mistake people make. Remember that not only does the alkyl group migrate, but the position of the positive charge actually migrates to where the alkyl group used to be. Okay, what's another mistake that people make? Okay, so let's redraw this compound here. A lot of people are going to use this compound to remove proton, okay? And this is also incorrect. Simply because this is not present. Look at these conditions up here. The idea that you could generate OH minus with that stuff present is it just doesn't make any sense. When you're doing a mechanism problem, you have to restrict yourself to the ingredients that you were given, and you're given strong acid. It's not likely that you could accidentally produce a strong base like hydroxide under these conditions. Okay, so you should show all of the energy minima in a mechanism problem like this. Okay, and you should be very careful to follow your arrows, is what I say. Most people can shift the alkyl groups, but a very sizable percentage of the class does not shift the positive charge. Okay? Alright, so just remember that you should do that. And I believe the next one is a dehydrohalogenation, and this is where we're going to stop this video right here. Okay? Alright, so escape.